Good morning class and welcome to our continuing lectures on sustainable energy technology. We have been discussing various types of energy storage technologies in the previous few lectures, and today we will start our discussion on electrochemical energy storage systems. We had previously covered mechanical energy storage systems and electrical energy storage systems. Each of these classes, as we have discussed earlier, are separated by the way in which the energy is being stored. For example, in the mechanical storage systems, you are either using the gravitational potential energy of water, the compression energy of compressed air, or the rotational kinetic energy of flywheels to store energy. Whereas in the various types of electrical capacitors that we discussed, we essentially stored energy as electrical potential energy between two charged plates that are separated by some sort of a dielectric medium. Today we will start electrochemical energy storage, which basically means battery-based energy storage systems. Battery-based energy storage systems are becoming increasingly common both in portable electronics as well as grid-based energy storage that is pairing with renewable electricity generation systems. This has primarily been driven by great advancements in creating better, more efficient and lighter batteries that can work well with different types of both user devices as well as storage applications. Now, when we think about batteries, we basically have two types of batteries. First type of batteries is what you would find in typical remote controls, etc., flashlights and other places. These are use and throw batteries, like the Duracell batteries that you might be familiar with quite a lot. You buy these batteries, put them in your portable electrical device. It runs the electrical device for some time and then the battery gets emptied and you throw it out. These are called non-rechargeable batteries or primary batteries. These are not very useful for any kind of energy storage option that we will be discussing, particularly related to renewable energy storage concepts. So we will not discuss these. What we will be discussing are rechargeable batteries that are also used in electronic applications like in your cell phones, your laptops, your UPS systems that are helping to keep your electricity on for your computers and desktops. These are called secondary batteries because you can recharge them using electricity. So they can store the electricity and they can then send the electricity to your device in times of need. These are also being used in renewable energy storage grids or electrical transportation technology. So like battery electric vehicles use these types of rechargeable batteries to power the cars, electric cars. So these are the batteries that we will be discussing primarily. We will be covering all types of them. Some of them are used for renewable grid storage, while some of them are more catering to electronic applications. Okay, so we will discuss that as well and why some are preferred for some applications and others are preferred for other applications. In today's class, we will primarily focus on the fundamental idea of rechargeable batteries, how they work, how they function, their performance characteristics, etc. So, batteries contain two electrodes of different metals. Usually when we are talking about different metals, it primarily means one is a metal and another is a metal oxide. Okay. We will see a very common example is a lead acid battery, where one electrode is lead, another is a lead oxide. Okay. So this is unlike capacitors, which uses same metal for both electrodes. Now this is generally true, but obviously when we looked at, say, electrolytic capacitors, this was not true. Okay, so but because you have a specific type of metal that is used as anode electrode in electrolytic capacitors. Okay. However, in general, capacitors use the same material for both its anode and cathode, whereas the idea of a battery is that the two electrodes are made of two different materials, and this is used. These two materials are performing two different functions. Okay. In between the electrodes, we have an electrolyte, which contains ions and electrons in solution. Okay. So we have an electrolyte between the two electrodes containing ions and electrons in solution. The electrolyte can be a liquid like a wet cell. So it's often if the electrolyte is liquid, we call it a wet cell, or a paste, in which case we call it a dry cell. Okay. So it can be a liquid electrolyte, or it can be some sort of a paste, a gel or a paste kind of a thing, in which case we call the battery a dry cell. So two electrodes, different types of electrodes, an electrolyte in between acting as a carrier of ions and electrons. Both electrons and ions can enter or leave the electrolyte solution from the electrode surface. So the electrode surface can either generate ions and electrons, which then go to the electrolyte, or can accept ions and electrons coming from the electrolyte. Okay. Inside the electrolyte, these ions and electrons migrate slowly from one electrode to the other. Okay. So if you see the electrolyte, there will be a transfer of charge from one side of the electrode, one electrode to the other electrode, through a transport of ions. Primarily it's ions, either positive ions or negative ions, from one electrode to the other. Okay. Now, what is the energy, type of energy that is coming from a battery cell? Okay. The electrochemical energy in an the electrical energy in an electrochemical system is provided by oxidation and reduction processes occurring at the opposite electrodes. So we are getting reactions that are happening. Okay. So the two electrode surfaces are sites of either an oxidation reaction or a reduction reaction. We call them half reactions because in one case the reduction reaction is happening on one surface and the oxidation reaction is happening on the other surface. The donor electrode is usually the metal electrode, and it delivers electrons to the external circuit. Okay. And this is during the discharge process. We will discuss this a little bit more detail later. And the acceptor electrode is usually the metal oxide electrode, which accepts these electrons. So we have a metal electrode and a metal oxide electrode, as we discussed. The metal electrode generates electrons, so it's an electron donor, and these electrons are going into the external circuit during the discharge process, whereas the acceptor electrode is the metal oxide electrode, which is accepting these electrons during the discharge process. In the charging process, the flow of electrons is reversed, and we will also see this in the figure, where the metal electrode is accepting electrons and the donor electrode is, the metal oxide electrode is generating electrons. But in the discharge process, when the battery is delivering power to the external circuit, the metal electrode is the source from which electrons are being generated and pushed into the external circuit, and the metal oxide electrode is the site where electrons are getting accepted. So donor, acceptor. The circuit is completed by a flow of either positive ions or negative ions between the electrodes through the electrolytic solution, and whether it's a positive ion or a negative ion depends on the specific pair of electrode materials being considered and the specific electrolyte we are discussing. Okay. So there is an external flow of electrons and internally there is a flow of ions, either a positive ion flow or a negative ion flow, depending on what type of electrode or what type of electrolytic material that we are discussing. Okay. Theoretically, if the electron donors, so this means the metal electrode is made of alkali or alkaline earth metals. So for example, sodium, nickel, lithium, calcium, potassium, etc. And if the electron acceptors are halogens or chalcogens like oxygen, chlorine, fluorine, these kinds of elements. So the first two columns of the periodic table for the metal electrode and the last two columns of the periodic table, halogens and chalcogens, for the electron accepting electrode. Okay. If this type of pairing happens, then you can get very high energy densities from your electrochemical cell or battery. Okay. This is because you have a natural affinity for the alkali and the alkaline earth metals to donate electrons, and a natural affinity for halogen and chalcogen elements to accept electrons. Okay. However, this is not always possible, because clearly if you think of chlorine and fluorine, it's difficult to create electrode materials made of chlorine and fluorine. But metal oxides, metal chlorides, these can act as a surrogate for those elements in the accepting electrode. Okay. So this figure kind of gives you the expected the maximum energy density that can be expected for different electrode pairs, and the corresponding maximum voltage that can be generated between the electrode pairs, as well as what is called a gram equivalent mass. Okay, so as discussed, the unit G equivalent is the molar mass divided by the transferred charge. So for example, if you look at this H2O2 system, which is completely impossible, you cannot have a hydrogen electrode and an oxygen electrode, but this is just an example. So 1 mole of water has mass of 18 grams. Okay. Now as one oxygen atom reacts with two equivalents of H plus, the equivalent molar mass is 9 grams. Okay. So because you have two charges, okay, between the hydrogen and oxygen pair, so that when H2 and O2 are reacting, you are producing water, which is the total, and the 1 mole of water is 18 grams, but two charges are involved. Okay, two positive charges are involved. So you have 18 by 2, so 9 grams. So that is the gram equivalent here that is being discussed. Okay. So obviously for hydrogen oxygen, it has the lowest gram equivalent, which is a good thing. So in this plot, what we are getting on the y-axis is the energy density of that electrochemical cell in watt hours per kg. How much energy such a cell can store. Okay. If the energy density values are large, then it's has a larger energy capacity. If it's small, it has a lower energy capacity, and the weight of the battery for the amount of energy it is delivering is quite large. Okay, so that is an important consideration. On the diagonal side is the voltage values. So what is the maximum voltage difference that can be sustained between the two electrodes? So this is also important for how much power it can deliver. So lower voltage is not a very good thing, like 1 volts, 1.5 volts. Higher voltages are better, 3 volts, 4 volts, 6 volts. Okay. You can see here, so apart from the hydrogen oxygen which has effect, lithium and fluorine combination, hydrogen fluorine combination, these sodium fluorine combination, so light alkali metals and light halogens. Okay, this combination provides the highest voltage and the highest mass specific energy densities. Okay. Below that you have the next set of heavier halogens and heavier alkali and alkaline earth metals like hydrogen, chlorine, sodium, sulfur, sodium chloride, lithium, bromine, sodium, bromine, zinc, oxygen, zinc, chlorine, etc. Below that you are getting lithium, aluminium, iron sulfide, lithium, aluminium, iron sulfate, etc. Okay. So these are specific combinations of alkaline, alkaline earth metals versus chalcogenic substances, okay, sulfides, etc. So these are providing medium values of mass specific energy density and medium values of voltage. Okay. Even lower than there are heavier elements like lead oxide. It's the common lead acid battery. It performs poorly in mass specific energy density as well as gram equivalent as well as voltage, but it was one of the earliest generated type of rechargeable battery systems, and it is still widely used because it has other advantages which makes it a good candidate for voltage for batteries. Okay. So practically used combinations include lead oxide, lithium sulfur, sodium sulfur, lithium polymer. We will discuss those. There is something on that as well. Cadmium nickel oxide based batteries. In general, electrode combinations that provide high voltage, high specific energy density and low gram equivalents perform better as energy storage systems. So we can see here in terms of watt hour per kg, these are the expected maximum values. So you get around 1000 to 2000 watt hour per kg, okay, values here. Alright. So you can compare these values again with the kind of energy storage densities that you can get from capacitors, from flywheels, or from pumped hydro based systems. Now here we are taking a look at the basic operation of a battery as it is getting discharged. So here discharge process, it is transferring energy to the external load. So here we have the load and current is flowing across the load from higher voltage to lower voltage. So energy is being transferred to your load. Okay. Now current direction is positive to negative. So ideally, which means positive charges are moving from the positive terminal to the negative terminal. Obviously, the flow of current is by flow of electrons, which are negatively charged particles. So the actual flow of electrons is from the negative terminal to the positive terminal, whereas the direction of current we say is from positive to negative. Okay. So electrons are flowing this way through the load from the negative terminal of your battery to the positive terminal of your battery when the battery is being discharged. Okay. Where are these electrons coming from? From the metal electrode. Okay. This is your metal electrode, the negative terminal of your battery. So here in this electrode, the metal electrode, electrons are being generated and these electrons are moving to the external circuit. And here the reaction is taking place where a neutral atom is being separated out into a positive ion and electrons. And these positive ions are flowing into your electrolytic system, electrolyte solution. And these positive ions are migrating to the other electrode where it is recombining with the electrons that is coming from the external circuit. So electrons move like this, positive ions move like this, and we have a recombination reaction at the positive terminal. Okay. So in the negative terminal, and this is called the anode, the electrons and positive charge are getting generated. Okay. So here how are we defining the anode and the cathode? So let's explain that a little bit. the anode is defined as the electrode from which electrons are entering the external circuit. Okay. Similarly, cathode is defined as the electrode into which electrons are coming from the external circuit. So anode is the source of electrons to the external circuit, and cathode is the source of is the sink of electrons from the external circuit. Okay. So as we see from the discharge process, the negative terminal is the anode during the discharge process of a battery. That is where dissociation reaction is happening. Electrons are being generated and positive ions are being generated. Electrons are going into the external circuit and generating the external current. Positive ions are flowing into the electrolyte solution and migrating to the positive electrode of the cathode through the electrolyte solution, where it is recombining with the electrons. Okay. This is the discharge process. Now we are discussing the reverse process, when the battery is being charged. When it is charged, a battery is using energy from the external source to recharge itself. So it is storing energy from the external source. So that means the external source is sending energy into the battery. Okay. So here again, just if you look at the figures, the positive and the negative terminals do not change. Okay. So this is still higher potential, this is still lower potential. Here again, higher potential, lower potential. Okay. However, the flow of electrons have reversed. The external energy is driving electrons from the positive end to the negative end. So basically the direction of current has reversed. So the direction of current is from the negative potential to the positive potential. And that is where you need the work. Work is being consumed to move the electrons up the potential gradient. That is from the positive potential to the negative potential. If you think of electron flow, and if you think of current flow, it's from negative potential to the positive potential. Okay. So work is being done on the battery. Alright. And battery is absorbing that work and using that work to transfer electrons from the negative terminal, from the positive terminal to the negative terminal. So now the negative terminal is the sink of electrons, and hence it becomes the cathode. Okay, because remember, cathode is where electrons are coming from the external circuit, and anode is where electrons are going to the external circuit. So the nomenclature cathode and anode switches between a recharging process and a discharging process. The electrode which is acting as the anode in the discharge process becomes the cathode in the recharging process, and vice versa. Okay, so here now in the positive terminal you are getting the dissociation reactions. Neutral atoms are being dissociated into positive ions and electrons, and the positive ions are flowing through the electrolyte going towards the negative terminal through the electrolyte, where you are getting the recombination. So in the previous case, recombination was happening in the positive terminal, and now recombination is happening in the negative terminal, and dissociation is happening in the positive terminal. So that is the basic structure of what is happening. What you are having effectively is the two reactions that were happening on the electrode surfaces are getting reversed during the recharging process. So you are getting back the original anode and the cathode material. Okay, during the recharge process that was getting destroyed during the charging, during the discharge process. So that is why we can have multiple cycles in a battery, because the material of the anode and the cathode transforms due to chemical reactions in the discharge process, but the reverse reaction is happening in the recharge process, so that the material is being recovered. Okay, then the cycle can begin again. Okay. So this also gives you basic idea of what does it mean for a battery to be fully charged or fully discharged. When a battery is fully discharged, all the anodic and the cathodic material has been converted by the reactions happening there. So there is no further atom in the anode, in the negative terminal, to be dissociated into electrons and positive ions. Similarly, there is no further atoms to be recombined in the cathode. Okay? And the full recharge happens when the reverse reaction is completed to full. So the full negative terminal, negative electrode material has been recovered and the full positive electrode material has been recovered. Okay. So that is what charging and discharging means. Okay. So today we will stop here. This gives you the physics of what is happening in a battery system. In the next class, we will look at the performance characteristics, current voltage characteristics, etc. for a electrochemical cell. Thank you for listening, and we will return in the next class.